So this is, we're going to include friction into our conservation of energy problems and then talk about a new thing called power. So here is a review problem. You should know how to do this one. It's still a little challenging, but if you did watch the videos and work on those practice problems, you do have everything you need in order to solve this problem. So we're looking for, there is a spring here. You might have to add that to there. So that block is attached to a spring. What we're going to do is we're going to take that block, we're going to pull it back, hold it there, just to the point where if we let it go, it moves through that circle just enough to make it around, okay? If we compress it any less, it'll just kind of go up and come back down. If we compress it more, it'll fly around there without a problem. So we're looking for the minimum amount of distance we have to compress this block against that spring so that it goes around that loop. What 2 points are we going to examine here? At the beginning, which is where the spring is, since we're looking for something about the spring. So we're going to look at that point. And where else? The top of the loop. Okay. Say it again. We don't know it, but we're looking for the minimum compression distance, which means at the top of the loop we are going to reach the minimum speed. So when it reaches the top, it does have to have some speed, or else it'll just fall straight down. And that is the minimum speed of the square root of GER. Alright, so we're always going to start off with our starting energy, and we're going to pick point A, and that has to equal our energy at point B. And that's just the total mechanical energy. What happens if the total mechanical energy is not conserved with that equation?
There will be less energy.
Yeah, that means EB will be less than EA. And that's whenever there's that thermal, or the work done by friction. So we're going to add that into the next problem. All right, but right now, there's no friction involved with this. The energy at any point is equal to the energy at any other point. Now what do we do to figure out the total mechanical energy at point A? We ask ourselves 3 questions. Is there a spring?
Yes.
So we write that down, 1/2 kx squared. Is it moving? No. Is there a height?
Yes.
No, it's at the lowest point.
Oh, I thought we were talking about the whole thing.
Now we're at point B. Is it moving? Does it have a height? Is there a spring?
No.
So there's our equation. So the unique thing about this problem, I'm going to rewrite all this. So the unique thing here is that that VB in the kinetic energy is going to be equal to the square root of GR. So making that substitution makes this a little bit easier to simplify down. So what's the square of a square root? It goes away. So this will just be GR, because you'll put in the square root of GR and square it, which is just GR. Okay. Then you can do your algebra. What happens in every... what doesn't happen this time? Mass does not cancel. Okay? Whenever there is a spring, the mass cannot cancel, because the force that the spring exerts on the block or object, whatever we're talking about, does depend on the mass of the block. So a larger mass will accelerate at a lower rate. All right, so that will affect the amount of energy transferred or stored in the spring block system. All right, so to simplify this down, I will multiply everything by 2. That'll cancel, multiply that by 2. Need to get x by itself. So x squared will equal mgr plus 2mghb. That's all going to be divided by k. And you can simplify that out a little bit more if you want to. So that x will equal the square root. I'm going to take out mg out of everything. So I have r plus 2hb over k, and you should get 0.78. On to the... All right, it's continuing on this. So there's a second part that says how high will it go after the loop, and for some reason that isn't cut off. So it's going to go up like that. And we're wondering how far up that hill it'll go. I don't know why that got cut off. So we start this problem the same way. Energy at one point will have to equal the energy at another. And I would pick whatever's easier, whatever's the least amount of work for you. You know information at the spring and at the top of the loop. So you can make the starting point either the spring or the top of the loop. But there's only one form of energy at the spring, so I would pick the spring. Maybe you would want to pick the top of the loop because the mass cancels out. I don't know. It's up to you. At the end, what type of energy exists? Is it moving when it reaches the highest point on a hill?
No, it's gravitational.
Does it have a height? Is there a spring? No. So we're just looking for that height. That would be your equation, because the energy at the beginning has to equal the energy at that end point. If you manipulate it, you should get that. And if we plug in our numbers, what should we get? $24 meters. To the next one. All right, hopefully that doesn't mess up the video. So here we have a car being released at the top of a hill at point C, and it reaches the bottom at point A, and we want to figure out how fast it's moving at point A. And the height is 10 meters, and the mass of the roller coaster is 250 kilograms. So how do we start? So the energy at the beginning has to equal the energy at the end. What type of energy exists at point C? MGH, because it does have a height. Is it moving? No. Is there a spring? No. At point A, is it moving?
Yes.
Does it have a height? Is there a spring? No. So mass cancels because there's no spring. Multiply this side by 2 and square root. All right, conceptual question. What would happen if I were to take an object and drop it at the same height at point C and calculate the speed that it would hit the ground at the same height as point A?
It would be the same.
It would be the same. Good. It would still be 14 meters per second. It would just be straight down. The equation is still the same. At the beginning, it's not moving, just has a height, no spring. After it falls down, once it gets here, no height, just has speed. All right, and it's just the directions are different. All right, The problem solving does not change. So now we're going to add friction to this problem. Same roller coaster. However, at point A, we end up with only 10 meters per second instead of 14 meters per second worth of speed. So we're trying to figure out how much energy is lost due to friction. So what changes in the equation? Well, the energy at point C is going to be greater than the energy at point A. So to make that an equality, you either have to subtract some amount from part C or add some amount to point A. It doesn't change what the equation is, all right, what the equation means. So you have two choices. You can either subtract what the friction would do to the beginning so that it equals the energy at the A. Some of you may think in that direction. I always write it as adding what's lost to the other side. They're both exactly the same. If you think about it algebraically, you just move one thing over and you add it, or you move this one over and subtract it, and they are the same thing. It's just how you view the situation and how you write out your starting equation. Okay? You'll always get the same answer. All right, so since the energy at point C is greater, I have EA plus the work done by friction. I'm just looking for that value. So I know that the work done by friction is going to be equal to the energy at point C, which, what form of energy? Just mgh, right? And then subtract what's at A, which is 1/2 mv squared, and our A value is going to be 10 meters per second instead of the 14. If we use 14, we get 0, which means the work done by friction is 0. There is no thermal energy created. There won't be any difference. If you put in 10, whoa, what happened there? You should get 12,000 joules. On the previous section, it said that the mass was 250 kilograms, so you can't cancel out the mass here because it's not contained in the work done by friction. So you have to include that. All right, so it says that the track is 20 meters long. There was a force of friction acting on it that removed 12,000 joules. What equation am I going to use to find the force? Good. So work done by friction is equal to the frictional force times that distance. They give us the distance. We just calculated the work done. Now we can solve for the force. We can get 600 newtons. All right, so some of this stuff isn't showing up. So we have a block on a track. It goes down like this, goes around the loop, and there is a spring here that stops the block from sliding. Right in this area, there is a rough patch that is going to be friction. Okay. Yeah, this area is only 2 meters wide. The height of the loop is 5 meters. And we want to find how far the spring compresses in order to stop that block after it has gone through the loop, past that area of friction, okay, hits the spring, spring's going to compress, slow it down, and eventually the block will stop and then be fired backwards. And It'll keep going until it falls off the loop. All right, so if we start at this highest point, I'll call that H naught for the starting height. That's supposed to be an H. At this point, what type of energy exists? Just MGH. And then what point are we looking at the end? So at the spring, what type of energy exists there? Just the spring energy, 1/2 kx squared. Do those two values equal each other?
No.
Why?
Because you lose some of the energy from the friction.
Friction has done some work. So you can either subtract it from the MGH or add it to the spring energy. Okay? Now we are looking for X. Right now we don't know the work done by friction. However, we have more information that is in the problem. We know that work is force times distance. Do we know the distance?
Yes.
Yes, the 2 meters. Do we know the frictional force?
No, but we know that mu.
We know Fun, right? So we know the mu. Do we know the normal force? It's on a flat surface.
I don't know what's
mg. Since it's on a flat surface and not accelerating up and down, that means the force down has to equal the force up. So the normal force equals mg. And just don't forget to bring down the distance for that equation. A lot of times people just write the frictional force equation but forget to bring down the distance. Now, we do have a small issue. What's our issue? We don't know H naught and we don't know X, so we have two unknowns in that equation. We can't solve for anything using that equation. So why do we waste all our time? Because it's still a correct starting point that most people, that's where they go. That's where most people will start. So we have to think of something else. We either need to know H naught or use a different point. So we can use the top of the loop. So at the top of the loop, okay, we have kinetic energy. What is that? And we have potential energy. And then that has to equal the 1/2 kx squared plus the work done by friction. Now remember that any point has to have the same energy, so the energy here has to equal the energy here. Right? In our original equation, what equaled this side was the mgh naught. Well, the mgh naught here equals the combined energy there. So you're really just switching out the values. This value is that value. So instead of using this equal to this plus that thing, just go from this to here because it's the same value. Solve for x. Speed here, the speed at the top is going to be the minimum speed because we're looking for the minimum compression. You're going to substitute in the square root of GER for that. So if you do some of the math, a lot of times you'll see a multiplication of 2 to cancel out the halves. So you end up with mgr plus 2 mgh minus 2 mu GD equals KX squared. You can plug in numbers whenever you feel like it. You can simplify that out a little bit by pulling out an MG if you want to. Just make sure you're practicing using your calculator, because people are still making calculator errors, but you'll get 0.37 meters. So that's about a foot, a little bit more than a foot. So the next part is what would be the maximum amount of force that the spring exerts. And that would just be, get rid of some of this mess. So the spring force is equal to K times X. We just found X. So the maximum force would end up at the maximum. I know that we solved for the minimum compression, but that would be in that situation, the full compression of the spring. All right, so you would have to use that total compression. What'd you get?
296.
Okay, just figuring out what the most amount of force that will be exerted on that block will be. All right, now some easy stuff. Okay. Power is the rate at which, interesting. Completely cut it off of this slide in the transition. All right, so power is the rate at which work is done. What is the definition of work? So remember, work is a change in energy. So work is not done unless the energy changes. Either changes form or changes in amount. So if power is the rate at which work is done, it is the rate at which energy is transferred. Okay? It's a rate, so power is equal to work over time. But since work is a change in energy, this can be written as the change in kinetic energy over time, or the change in potential over time. And that potential could be both gravitational and or spring. So work done is a change in energy. It's a change in any type of energy. The units so since power is work over time, the energy of work is joules per second, which is equal to a capital W. Don't get confused with work. This is a watt. So you've heard of watts in electricity, light bulbs.
So what's capital W?
Watt is a capital W for the unit. Okay, so make sure, so the unit of a watt, which is a capital W, is the unit of power, which is a capital P. Variable, unit, okay? Where work is a capital W for the variable, but is a capital J for the unit. So don't get the units and the variables confused.
Wait, so work is a capital W?
Yep.
Mark is.
No, I can't write.
Hold on.
All right, so here we have a car that has an engine that has 190,000 watts of power, and it can accelerate from rest to a top speed in 9 seconds. How much work does this engine do? So power equals work over time. It asks for work, so manipulate that for work. As power times time. Take your 190,000 watts, multiply it by 9 seconds. 1,710,000 joules. Yep. All right, so here's another engine. It reaches its top speed in 7.5 seconds from rest. This can perform 250,000 joules of work in that time. What's the power of the engine? So power equals work over time. They tell us the work. They tell us the time. Watts. Here we go. If a runner exerts 350 joules of work to make 125 watts of power, how long did it take the runner to do that work? So always, hey, I read power. Let's write power equals work over time. They want time. Manipulate our 3-variable equation. Work over power. $350 joules, 125 watts. 2.8 seconds. All right, so here is a situation. So if I take Hero, I know that the video can't see this, but I have him at the bottom of the chalkboard. I lift up Hero, and that took 2 seconds. How much power did I exert? It's asked for power, so of course just start with that power equation. Work is the change in energy. What type of energy is changing? Gravitational potential, which is mgh. So if I make the bottom a reference point of 0, all right, because I'm only going 1 meter above that 0 point, we would have mgh minus 0. Okay, if it's going between any 2 points that have a value, you would have mgh minus mgh naught over the time. Okay. I forgot to write down the mass of Hero. So 0.3 kilograms. That just looks terrible. What's the value? 1.47? Now, what would happen if I do the same thing in half the time? What would happen to the power if I did the same thing in half the time? Yes. The power would be doubled. Two ways you can look at that. Just divide the time by 2, so you get the top over the bottom, which is 1. You get twice as much, right?
Thanks.
The other way is just to look at the equation, right? If this goes down, that has to go up. and you can start to quantify it by, oh, I decrease this by a half. That means I'm basically doing a 1 over 1/2, which is equal to a 2. So everything would go up by 2. Let's look at it a little differently. Now I lift Hero up that same distance of 1 meter, but I'm lifting him at a constant speed of 2 meters per second. How much power did I exert? So first, let's just start with our power equation. This one I have to kind of run through with you. I'm going to write the work. I know it's a change in potential, right? But I'm going to write it as a force times distance. And if we think about that, this force and that distance is equal to mgh, right? Because the force, if he's moving at a constant speed, has to be equal to mg, good, right? The upward force has to equal the downward force. So the weight is down, my upward force has to be equal to the weight in order for it to move at a constant speed. So F would be mg, the distance it travels is the height, so it would just be mgh. Now, do you see anything else in that equation that is good? Distance over time is constant speed. So this equation for power is used for anything that has a constant speed. This whole part, the distance of 1 meter, will probably not even be written in the question if you see something like that. So I lift up Hero at a constant speed of 2 meters per second. How much power did I exert is really all you would need to know. The upward force has to be mg. Speed has to be 2. So what is the power? All right, so that's really as hard as it gets for power. Really for almost anything. We've seen like the hardest problem, which is that spring coaster, right? And remember, that will be on the test. Some form of loop, spring, hill combination with friction.